What you're looking at on this glorious Sony CRT TV is high definition video. It's higher definition than DVD. It predates DVD, at least the underlying format does, by about 10, 15 years, and it is completely analog. I'm talking about the high vision system that was invented by NHK in Japan in the late 70s, early 80s. They had grand visions of it taking over the world in terms of being a high definition video format. And their last dying gasp of this process was the VCR that you see above me now. That's the JVC Victor HR-W5, a Japanese VCR that recorded and played back high definition video completely from analog tape. It's basically a VHS tape with some special features that we'll talk about in this video. Now, WVHS, there's not a ton about it on YouTube. There's one really good video from Cathode Ray Jude where he goes through sort of the high level sort of system overview. But today I want to open this device up, look in its guts and show you sort of how analog video is recorded in this amazing resolution on analog magnetic tape. It's a cool journey, so stick around and let's open this puppy up. Gotta say, you'd think in my line of work I'd be pretty good at recording video off a TV, but I was in such a rush to get this guy open to show you what's going on that I kind of winged it. But it looked glorious, absolutely glorious on the screen. But debating what's more glorious, what the picture looks like or what we look like in here. There's a lot to go through in here. I'm not going to go through everything, but I think I should probably start at a place a lot of good beginnings begin, which is with the tape itself. This is not the original tape that this deck was specified to use. This is a more modern tape. You see it's a digital S-video tape. It's used for digital video recording, but typical VHS signals are recording, less than 5 megahertz, depending on PAL, NTSC, frame rates, that sort of stuff. WVHS, which is what this device is, and what you'd originally use would be a WVHS tape, is capable of recording sort of 20 megahertz of bandwidth, so 5 times more bandwidth to capture that high resolution image. And the first way that it does it is with the tape itself. So if you're not familiar with VHS tapes, they are magnetic tapes, similar to audio tapes or reel-to-reel tapes, which you may have seen. They have sort of magnetic particles on top of the plastic tape that record the signal in the magnetic domains. Now, this is wider than a regular, say, audio tape, but it's the same width as a VHS tape. To my eye, that's 1/2 inch. And what makes sort of these tapes special as opposed to normal VHS tapes is that magnetic domains, the particle size on the tape is significantly smaller. If you imagine that each of the domains is like a little magnet that can be sort of moved around by the magnetic recording head, the smaller the magnets are, the more resolution. Now, like a regular VHS tape, it records on angular stripes along the tape. That's why you'll see the tape head here is at an angle. So the tape runs this way, but you've got these long parallel lines. Or helical tracks allow the tape head to spin relatively quickly compared to a relatively slow moving tape. So rather than having to zip the tape by very quickly in the transport and putting a lot of wear and tear on a tape, you've got the tape moving slowly, the heads are moving quickly, which means you're using the full area of the tape rather than just a straight line to capture more bandwidth. Now what WVHS does is it introduces the idea of a second stripe. It splits up the video information from a composite signal that you'd have in VHS where luma and chroma are sort of intermixed together, and it records separately the luma, the PB and PR information, and that gives you more bandwidth for each of those and gets you a much higher quality video signal. Let's have a look inside and I'll start to show you some of these signals. So here we have the drum. As you can see, it's tilted at an angle. I really don't want to touch it. But if you look down the bottom, you can see maybe these little black gaps. These are the read-write heads. You can see how many heads there are around this, whereas a normal sort of VHS tape will have one head. These wide slots here, I don't know if you can see those, contain the 2 heads that are slightly offset for the parallel track recording. We have the mechanism up here for controlling the drum motor. Over here we have our power supply. This large board here pops out easily, and it is the tuner unit that picks up Japanese TV. They did sell a few of these units in America, primarily for sort of professional applications, medical image recording, stuff like that. didn't include the tuner capability. But the drums send their signals through to these two boards here. This first board here is a preamplifier. Then we have these other sort of post amplifiers that send out through these two connectors here an FM signal. VHS tapes, SVHS tapes use frequency modulation. In fact, all videotapes, all tapes use some sort of carrier frequency to encode the audio or the video. That's because magnetic tape, the principle behind it is a changing magnetic field results in a voltage or an electric field. And so if you have a DC voltage, you get no changing magnetic field, which means you lose DC. Also, tapes, the magnetic material, the magnetic domains are highly nonlinear. They have hysteresis. And so by encoding things in some sort of subcarrier, it's sort of called a bias signal, I think, in audio tapes, and that's around 100 kilohertz above sort of the human hearing range. And it's significantly higher in this deck. You get to encode possibly DC signals, which are required for video. For example, a flat color screen is just a DC signal for every scan line. If you've got a solid gray or a solid red or whatever, you want to be able to encode that. And so you need to have some sort of carrier. And so here we're using frequency modulation. And so we have luminance being split out over both of these and chrominance being split out over both of them too. In fact, if you disconnect one of these RF connectors, you get the same sort of picture out, but you lose half your resolution. I'll show that to you at the end of this video. Then they go down underneath the bottom of the device to where we go from the frequency domain RF signal into component video. So let's flip this guy over and take it apart. All right, inside this well-shielded metal can is the heart of what makes WVHS WVHS. You've got the FM signal that's been amplified coming from the read heads, coming in through, I think, these cables over here. Yeah, these thick ones down here. And they're going into this can, and here we've got the magical board which outputs the component video and inputs component video. How do we go from FM to component? Well, let's open up this tin and try not to bend it. Here is the double-sided magical board. Let's start on the back. These two JVC chips here are responsible for receiving the two FM encoded signals and demodulating them into their baseband signal. So you get one stripe going in here and one stripe going in here. Then the demodulated signal comes out, flips over the board. So these two chips are analog to digital converters. So it takes the demodulated FM signal, converts them into parallel binary data, 8 bits per chip, and it goes into this big bad boy here. It takes that and stores the data in this RAM here. In Gravis's video, in Cathode Ray Dude's video, he talked a lot about how, this is technically analog, but it feels very digital in terms of the artifacts that you get. And that's really because of what these chips need to do to unscramble the analog information that's stored on the tape and present it in time for the component analog video signal going out. There's frame buffering, there's temporal sort of denoising, so going on between frames, and there's a lot of error correction and noise handling that has to happen in case the signal that's coming through is not quite kosher. And it's doing that in the digital domain, which means the sort of artifacts that you get are pretty digital. I didn't work this all out myself. There is a service manual online. I wouldn't really call it a service manual. It doesn't have schematics. It's got sort of block diagrams and the language in it. It's very marketing-y, talking about how great this all is. But it gives you enough to get a sense of what to look for at least. And would you like to see the actual signals in here? I know I was certainly eager to, so let's do that. Let's go have a look at the actual FM signal and the analog signal before it gets turned into the component video signal, so we can see what's actually happening on this tape. All right, I think we're in. What I have done is soldered a BNC cable to points where the FM signal comes into this board. Let's have a look on the scope and I'll show you what we see here. And we can see a signal that's around 8-9 megahertz. Scope's not really the right tool to be looking at an FM signal, but I do have a spectrum analyzer. So here we are plugged into the spectrum analyzer. I'm looking between 2 megahertz and 20 megahertz. You can see some of the carrier frequency from the circuitry in here already bleeding through. If I press play on the tape, we shall see a signal come up. Here you can see in the spectrum monitor, we have the FM signal here. I'm not going to decode this. That's what these chips are for. But you can see clearly there is a signal here that is frequency modulated, moving back and forth. You can see that spectrum sort of widening up from the carrier that you had before. Let's now look at the output of this chip here, which is demodulating that, and we'll get something that looks a little bit closer to a component video signal. This is looking at the demodulated signal, and here is a test pattern on the screen, and the video will start in a second. This looks very much like a component video signal. Let's see a couple of scan lines, maybe zoom in this direction, and let's pause. So what we're looking at here is 3 horizontal scan lines. Here you can see the sync pulses, and it looks kind of like a regular component video signal, but it's a little bit different. You'll notice the sort of back porch and front porch is missing, and you've got 2 different levels happening here. I think what's happening is this is the luma information, and this is PR, and then PB is on the second chip. So I think they're cramming, by reordering the signal information, they're cramming PR, PB, and Y all into 2 stripes. It's being then digitized by the analog to digital converter, stored in the RAM, and then the CPU that's on here. Well, it's not really a CPU, it's an ASIC. Reorders those frames to get the YPB and PR all appearing at the same time. I think an interesting next step to do with this would be to capture these analog signals that you're seeing on the screen now and load them onto the computer and try and decode a frame in software. That would be interesting. It would also be a fair bit of work. I've done that for regular component video, but I think this video is probably long enough as it is, so maybe we should spend some time looking at the glitches that you get with this, because those are pretty telling and reveal a lot about what's going on in the digital domain to get the analog video out as analog video through a whole bunch of digital jiggery-pokery. So let's put this guy back together and glitch with it. So here we have the video from before. It's looking pretty good on the screen. You're getting some smearing as expected from the lower bandwidth. Let's try glitching this out. Here I am just bringing my hand close to the drum, and you can see those horizontal artifacts coming in. And if I slow the drum down with my finger, you can see the blockiness as the digital chip that's trying to reconstruct this signal from the frame buffers is really struggling. It's doing a bunch of interesting stuff to be resilient from noise and to reconstruct things in the time domain. It's looking between frames. You can see sometimes when you pause, you get bands from where the frame buffer is reading versus writing. Let's try with the jog wheel. I don't know if you can see down here, you've got different frames appearing at different points on the screen. And you can see the interlacing as well. But that's expected because it's an interlaced format. The other thing I want to show you is, let's get the video playing again. Should I be doing this live? Yeah, why not? Let's take out one of the RF signals. I'm going to pause it at the very least. So you can see here it's coming from a frame buffer because, you know, touching the drum does not glitch out the video because it's coming from the digital domain. Alright, we've removed CN203, which I think is one of these is the main and the other one is the sub of the two stripes. One of the stripes on the tape is considered main, the other one's sub. If I hit play, the video plays, but I don't know if you can see this. It's at half resolution, so you've lost both luminance and chroma in half the resolution. If obviously only luma or chroma was on one of the two stripes, you'd lose the PB or the PR. Actually, let's go back to the test pattern. That's interesting. In fast forward rewind, it's getting some of the color information because I think the stripes are going by. But if we just go frame advance, we've clearly lost PB. So there goes that theory. Yeah, no, that makes sense. So you've got Y on both of the magnetic stripes and you've got PB on one and PR on the other. So that must have pulled out PB. Yeah. Yeah, that makes sense. All right, I've been at this for a while. Hopefully this video is interesting to you folks. I know I'm blurry here, but I wanted to keep the picture sort of pretty. Anyway, hopefully this is interesting. I might pack this all up and get back to my other projects. I'll give you an update on Scion pretty soon. See you next time.